Hello students, welcome to CSIR online coaching. I am Adityavardhan from adichemistry.com Warangal. In this presentation, you are going to learn about Jablonski diagram that helps in understanding the photochemical processes and fluorescence spectra. It is for IIT JAM, CSIR NET, GATE and other university level examinations. Okay, now this is the Jablonski diagram representing various electronic levels in the molecules and different types of radiative and non-radiative transitions occurring between them. Looking complex? Don't worry, I will make it easy for you by constructing this diagram step by step, so that you can not only understand this diagram but also remember it forever and apply the concept in various photochemical processes whenever required. Let us start our journey by drawing singlet electronic states which are represented as blue colored horizontal lines. These are indicated by the letter S. The energy of these states increase from bottom to the top. The singlet electronic ground state is denoted as S0, while the excited singlet states are represented by S1, S2, S3, etc. Remember that in a singlet state, the total spin angular momentum will be 0 as all the electrons are paired up. The diagram also represents various vibrational levels for a given electronic state. The ground state vibrational level for a given electronic state is shown in as a thick line. In the same way, the triplet states are also represented in Jablonski diagram. Here, these are denoted by the letter T and are drawn in orange color. In the triplet states, the total spin angular momentum is equal to 1, since the two electrons have parallel spins. The triplet states are associated with more energy than the singlet states. And upon careful observation, you can find the energy gap between successive electronic levels in both singlet and triplet states decrease from bottom to the top. It is also valid for the various vibrational levels within an electronic state. The vibrational levels become more closely spaced as energy increases and eventually form a continuum. For clarity, only a subset of these vibrational levels are represented on the diagram. When the molecules are supplied with energy in the form of light, the electrons will be excited to any of the higher energy levels depending on the amount of energy associated with photons. These transitions from lower to higher electronic states are represented as black solid lines. Remember that in Jablonski diagram, the radiative transitions are represented as solid lines. Keep in mind that the radiative transitions are the transitions that occur due to either absorption or emission of photons. On the screen, a few of the possible transitions from the ground electronic state to different singlet vibrational levels are shown. At room temperature, the majority of molecules in a population will be in the lowest vibrational level of the ground state, and therefore absorptions are shown to start from this level. These radiative absorptions are the fastest transitions in the Jablonski diagram and occur on a time scale of order 10 power minus 15 seconds. Now you may ask, what about transition to a triplet level? The direct excitation to the triplet excited states is not possible due to conservation of angular momentum. Therefore, we do not represent this transition from singlet to triplet state on the Jablonski diagram. After a molecule has been promoted to an excited state by absorption, it is in a non-equilibrium state and will eventually dissipate the energy that it has gained and return to the ground state. There are a multitude of ways that energy may be dissipated. The first is through vibrational relaxation, a non-radiative transition to a lower vibrational level within the same electronic state as shown on the diagram using squiggly or undulating arrows. The non-radiative transitions are the transitions that occur without the absorption or emission of photons. In this process, the excess vibrational energy is lost to other vibrational modes as kinetic energy within either the same molecule or to surrounding molecules until the lowest vibrational level of the electronic state is reached. The vibrational relaxations occur on a rapid time scale of 10 power minus 12 to 10 power minus 10 seconds and outcompetes all other transitions except absorptions. If a non-radiative transition occurs between two electronic states of the same spin multiplicity, we call it as internal conversion. These are also represented by squiggly arrows as shown on the diagram. The internal conversions occur mostly between higher lying singlet excited states since the vibrational energy levels are strongly overlapping. The rate of internal conversion is inversely proportional to the energy gap between the two electronic states. They usually proceed rapidly on a time scale of 10 power minus 11 to 10 power minus 9 seconds. However, since the energy gap between S1 and S0 is much wider, the internal conversions between these states occur on a slower time scale. And remember that internal conversion is immediately followed by vibrational relaxation to the lowest vibrational level of the electronic state. One more possibility is a non-radiative transition known as intersystem crossing between two isoenergetic vibrational levels belonging to electronic states of different spin multiplicities as shown on the figure again by squiggly arrows. In this case, the electrons are shown to undergo transition from a singlet state to a triplet state. In principle, these transitions are forbidden due to conservation of spin angular momentum. However, the spin-orbit coupling between the spin angular momentum and the orbital angular momentum makes them weakly allowed, especially in the molecules with heavier atoms. These transitions occur on a time scale of 10 power minus 10 to 10 power minus 6 seconds. After intersystem crossing, the molecule will immediately undergo vibrational relaxation to the ground vibrational level of respective electronic state. Now we will deal with the fluorescence and phosphorescence. The radiative transition from a higher singlet state to the lower singlet state, especially to the ground state, is known as fluorescence. It occurs on a time scale of 10 power minus 10 to 10 power minus 7 seconds. As a consequence of rapid vibrational relaxation and internal conversion processes, the fluorescence occurs mostly from the lowest vibrational level of the first electronic excited singlet state S1 to the singlet ground state S0. These processes are also responsible for the Stokes shift, where the fluorescence occurs at a longer wavelength than the absorption. While the fluorescence is the transition between two electronic states of same multiplicity, on the other hand, phosphorescence is a radiative transition between two electronic states of different spin multiplicities. Just like intersystem crossing, phosphorescence is, in principle, a forbidden transition, but it is weakly allowed through spin-orbit coupling. It occurs on a much longer time scale than fluorescence in the range of 10⁻⁻⁶ to 10 seconds. So this is our final Jablonski diagram, constructed step by step. That's all for now. Visit adichemistry.com for more information on this topic, or search for adichemistry CSIR net for NTA CSIR net and GATE chemistry study material. All the best. Don't forget to subscribe to this channel, like this video and share it with your friends. Don't forget to write a comment.